Okay, so let's talk a bit about parsing and my parsing library. So, like, what was the story? So the story is that library is called flatparse, and you can find it on Hackage, and there is already the 0.1.1.1 version is already up on Hackage, but it's kind of work in progress because the documentation is kind of sparse, and also I want to have a bit more examples, and I want to do like kind of more informative tutorials, and yeah, so I want to demonstrate some features, and maybe also add a bit more features, like more error kind of infrastructure for errors and infrastructure for indentation parsing, because right now the way it looks is essentially you can implement whatever you want, but it's not batteries included. So in the library there is only like the basic infrastructure, and if you want to implement some more sophisticated features, then you have to do it. But let's start from the beginning. So I kind of like wrote like the core of this library about like 1 year ago, but then I was just looking at how to do parsing for my setoid type theory implementation, and I wanted to make it generally kind of fast and also nice, but the issue is that if you look at the actual Haskell parser library, so what kind of libraries are there? So there are Parsec, okay, so there are also up to Parsec, but I can also just quickly summarize like how these work. So Parsec is kind of ridiculously slow. So if you write any parser in Parsec, not even the monadic binds are going to be inlined. So this is ridiculously slow. I was even able to do a micro benchmark when the difference between flatparse and Parsec was 1000 times. So Parsec was 1000 times slower on some kind of like comma separated values parsing or some kind of keyword parsing than flatparse. So it's crazy slow and kind of old, and also yeah, I mean, but you can use it. I mean, it's completely practical as far as just writing parser go, if you don't care about performance. So there is
Why is it problem if something is old?
Sorry?
Why is it problem when something is old?
Okay, I mean, it's not a problem actually. I mean,
Okay.
because if it is old, it could be good, but because maybe if it's old, then it has been refined for a long time, but it seems it's not the case. But I agree, it's not a negative if it's old, but maybe it could be a negative thing, because I mean, at the time when Parsec was implemented, there were some GHC features. I mean, some GHC features were not available. So, for example, they couldn't use like unbox tuples, which is very critical in my implementation of the parsing library.
Yeah, that's a design issue. It's not the age, but it's like
Yeah. Okay.
worse design or not not utilizing the modern features or something.
Yeah. Okay. So Parsec is really slow, and for some.
Sorry, another question before we go into more details on a much wider point of view. So, what are our expectations regarding the performance? How do we expect? How much time do we expect to be spending on parsing versus type checking versus compile time evaluation? Roughly. So what we are expecting to be the bottleneck? Because if type checking is expecting to be the bottleneck, then the parsing is not really an important point.
It's a very good question. So what I can say is that so this is a very good question, and clearly I would not be interested in in good parsing libraries if this was not a problem. So one example I can give is that I have like this. Now it's kind of it's even a bit suboptimal and outdated implementation, but I have like this multi-t, which is a demo for like fast elaboration. And in this case, by switching from Megaparsec to flatparse would make like the whole elaboration process, including parsing, more than twice as fast.
And this is the overall, so
This
it includes everything, right?
So this is parsing plus elaboration plus also printing out the output of the elaboration.
And what kind of programs you were using to measure this? So roughly.
It's not, doesn't have to be very sophisticated. You just take a source file which has like 100,000 code lines, and I don't think you have to be super sophisticated to measure time. You can just use wall time, and that's pretty much it.
So what is causing me confusion is that usually we are talking about all these exponentially blowing up evaluation steps, whether inside type checking or during evaluation, where we are substituting stuff into definitions, and we are always talking about how these blow up. And compared to these, the original source code could be very, very small. So either these are in two different orthogonal directions, or these are not representative of the codes that we would like to actually compile at the end during normal use cases.
The blow up is a problem which is to be solved. But if you can solve the blow up in like most practical cases, then what you actually get is the absence of blow up, and you have fast elaboration. And if you have fast elaboration, then the performance of elaboration, like for example, the reason that I get this speed up in small tt from fast parsing is because my elaboration is so fast that it's comparable to Megaparsec.
Okay. So you have gone so far that now the parsing is a limiting factor for you.
Exactly. So
okay.
Actually, if you do elaboration in the right way, it could be faster than writing an idiomatic Megaparsec parser, and then you are slowed down by Megaparsec significantly.
Okay, thank you.
Yeah. Okay, so there is Parsec, and an interesting, like a historical bit about Parsec is that at some point, but there was recently some Stack Overflow question when there was some answer which kind of went into the details. So the question is, why is Parsec CPS encoded? And it seems that so Parsec uses this CPS implementation, and it seems that the reason is that at some point some implementer thought that it looked nice, and he benchmarked it, and it seemed to be roughly the same performance, but there is no very strong reason that why Parsec has to be a CPS implementation, and it was quite a while ago. But after this, for some reason, all the parser libraries by default started out with a CPS implementation, even though there was no super strong reason why to do that in the first place. But then Autoparsec also used kind of a CPS, and so Autoparsec is resumable and also CPS, but not really suitable for programming languages, because like error message and source position, source span, indentation, whatever. So like there aren't really enough features to do programming language or human readable format parsing in Autoparsec. So this is supposed to be kind of a high performance, more more like kind of a data parsing stuff or binary parsing. And not really language parsing. But it turns out to be that Untitled is way slower than what is possible to implement, even just for binary parsing. And like for example, if I want to parse, so flatparse by default is kind of a UTF-8, but even if you use flatparse to parse just bytes or ASCII, then it's usually at least 10 times faster than Untitled, which is supposed to be the high performance library for data parsing. So it's still not very fast. So there is Parsec, there is Parsec, and there are some kind of fringe stuff, like fringe modern. So there was this parsnip, which is not even published. It's just, I mean, they're not even published on Hackage. It's by Edward Kmet, and it's just in some random repository in GitHub. And actually, I haven't benchmarked this, but it seems to be very similar to flatparse in some respects. So this is like the high performance, like kind of raw data parsing, but still not for language parsing, because this is very minimal and this is super focused on high performance. But just by looking at the implementation, it's very clear to me that this is the real deal. So this should be comparable in performance to flatparse, but even more minimalistic. So it's not focused on language parsing, just on raw byte parsing. And yeah, and there is also Bytesmith, which is actually, I mean, both in performance and in scope, it's kind of similar to Parsnip, but I think it's probably slower. So it has kind of a different internal representation, and there are some features which are not supported here and also not supported here, and maybe because of those features it's a bit slower. But maybe it's just not optimized well enough. So maybe if you optimize, or you would optimize the implementation of Bytesmith, then it would be similar to flatparse. I'm not sure. I only did a very small amount of benchmarking with Bytesmith. Yes. Okay, but the point is that there is no high performance parsing library with good support for programming languages, so that's what I wanted to do. And there are some kind of general observations. The trifecta, it was I looked at this library a very long time ago, but I'm pretty sure that trifecta is quite slow. So it has very fancy features, uses some very fancy data structures, but I find it very likely that it's like comparable in performance to maybe Megaparsec.
And what about, have you looked at Parsley? Which, I mean, to me, the interface to Parsley looks unusable, but given that they have access to pretty much everything at compile time, it could be fundamentally faster than Combinator.
Parsley is the stage selective.
Yes, that stuff, yes.
Yeah, I looked at
I wouldn't want to wish it on my enemy to use it, but...
So, yeah, I looked at it, and it absolutely makes sense. I mean, I read the paper about stage selective parsers, and it's completely fine, but and it would be interesting to combine stage selective parsing with flatparse as a backend, because so in this party library what happened is that we have kind of a template Haskell interface to parsing. So there is a kind of a template Haskell interface plus different backends. But right now the issue is that like the staging of all of these parsers, you can look at the paper for the improvement, but it can realize like a several times speed up if you do this compile time optimization of your selective parsers, which is pretty good. But the issue is that if the backends are just Parsec or Megaparsec or Parsec, then it's still way slower than just writing naive parser in flatparse, because in flatparse, like on micro benchmarks of flatparse is about 10 times faster than all of these. But if you add more fancy features, then it's about like maybe 30 times faster if you also want to have source position spans and indentation parsing. So it's not nearly enough to have like a 2 to 5 times speed up using staging, because the backends are still so slow. But it would be interesting to try to have like a flatparse backend for parsing. But maybe, I mean, at this point probably it's not worth the effort, because I mean it's good enough if you are just writing a naive thing in flatparse, and then you have actually pretty good compilation times as well, because so this is like super tight and uses premops and very like a very compact code output which we get from flatparse. So usually the compile times are also pretty good. But if I want to do compile time optimization, then maybe the compile times would also suffer. So there is a trade-off. But if we live in a world where actually a template Haskell interface is a more sensible staged programming interface, and the compile time evaluation is also very good, then probably it would be a better user experience. But the idea behind it is pretty interesting. So maybe this would be another thing to try if we have the programming language with the nice staged computation, to try to do the staged selective parsing in that setting and not with template Haskell. Okay, so like what are the guiding principles? So one guiding principle is that like I only want to cover maybe about 95% of all like programming language parsing use cases, which means that I focus on UTF-8 and no resumption. Maybe I can talk about it. I mean, it's possible to add resumption, but it's not the typical use case if you want to parse programming languages. So no resumption, and right now only strict bystring input. But this still means that you can convert, like you can still parse any kind of data if you can turn it into a strict bystring. So we can still just turn text or whatever to bystring and then parse the bystring, and probably it would be still faster than most of the alternative solutions, because the conversion can be done very quickly, and we have a much faster parser if we are working on bystrings. Okay, so only strict bystring input, and it means that we also do not have like no generic implementation. So the implementation is not generic. So implementation is not generic over like streams of inputs, or we do not have like a parser transformer, monad transformer, and the reason is that I mean it's a fringe use case. It's usually not needed, and I mean it's very rare that it's actually needed. But if you don't need it, then it very reliably wrecks GHC optimization abilities. So if you are using like something defined as a monad transformer or something which is generic over like lots and lots of type class instances and dictionaries are passed all around the place, then I can pretty much guarantee that at some point the optimization is going to fail in some ways. And this would be another thing. So if we worked in the hypothetical language with staged computations and staged compilations and with like completely typed formal guarantees about what kind of computations and what kind of arguments disappear after staging, then this would be a completely 100% acceptable solution and implementation in the library. So if we had this programming language, then there would be no issue with this genericity at all. But if you are working in Haskell, then this is actually an issue, and the overheads cannot reliably be removed. So this is like this, and then, okay, so what about like error messages, indentation, and source positions and spans. Okay, so what about this? And okay, so with error messages, I can just briefly talk about what I don't think is the right solution. So maybe let's write a couple of words about Megaparsec here. So this is kind of a newer implementation of which is very similar in style to Parsec, but so this is faster than Parsec, and it's roughly as fast as Parsec, but focused on programming languages and like it's more richer in features than Parsec, but is roughly has the same performance. Maybe if you don't optimize your Megaparsec parser, then probably it is slower than an Parsec, but you can just optimize it and it will be comparable to an Parsec. Okay, so faster than Parsec, and like it's kind of richer in features. Okay, like but what kind of implementation we have in Megaparsec? So in Megaparsec, the way error messages work is that there is some kind of built-in automatic hint propagation. So you write some parser and then you do some testing run, and then you get some error messages, and the error messages are like not completely bare bones. They contain some information, so they contain hints, and the hints are like expected, like a whatever keyword or another keyword or another symbol or another symbol, and it just lists out like a list of things which are expected at the point of your parsing error, and this is kind of a deeply built-in feature, and you cannot disable it. So can disable and has a very large overhead, and I mean, like you cannot disable this implementation of hint propagation, which is like hardwired. Of course, you can write your own error messages and you can build on top of this mechanism if you want, and then you get much better error messages than by default. But the point is that there is a default mechanism which is always there, and it always has a large overhead, and by itself is just a toy implementation. because if you write a larger parser for like a more complicated language, then if you only use this built-in hint propagation feature, then you don't get very harmful error messages, because it just barfs out like a very long list of what kind of things are expected. And if you like get a list of 30 symbols which are expected, then that's not very helpful. So you still have to do something on top of it. Okay, so my reasoning is that what I want is minimal overhead of fancy errors if you don't want fancy errors. But at the same time, I also want to have a possibility of fancy errors if you want them. But then mostly you have to implement it yourself. But it should be possible to put some kind of particular solution in the library, but right now there is no particular solution in the library. There is just some demonstration in a tutorial folder which gives an example of how to do somewhat fancy error messages. But I haven't yet decided on what to do. And likewise, I want to have a minimal overhead of source position tracking, but the possibility of kind of like very ubiquitous source position tracking. So if you want to do a parsing which is aware of source positions, then the right solution is just to like completely annotate your syntax tree with source positions, such that you can always recover the span of any parse expression from the original source file. So you should still have the possibility of like pervasive source position tracking, spanning, but still in a very efficient way and exactly the same way. So I want to have fancy errors, source position tracking. I want to have indentation parsing, but also I want to have all of these things in a way such that if you don't want to use them, then you get almost no overhead. So kind of the same way. Okay, and right now, so the library is structured in this way. So there are actually two modules. There is flatparse basic, and which has kind of, I mean, no possibility of doing indentation parsing. And this is very slightly slower. And at this point we can probably just look at the definitions of like what parsers are. So if we go to this basic, then so this is like the definition of my parser type. So if you look at this new type parser, then there is a reader environment, and there is also a type of errors, and there is a return type, and on the inside we have this function. So the function takes a foreign pointer content and like one R from the reader environment, and then this address points to like, so this is like the pointer to the end of the buffer. So this is just a pointer which points to the end of the byte string, and this points to like the current position in the byte string, and then we get a result, and the result is an unboxed tuple which has these 3 constructors, and for that I mostly just use pattern synonyms. So there is an OK case, and the OK case contains a return value together with the new address, like the new current address. And then this is the error case, and then there is also a failure case, but later I will talk a bit more about like why should we have this distinction between errors and failures. And this is the implementation of a parser, but I have to note that we have these 2 things as function inputs, and then the question is, why should I include just one random reader environment in this parser? So can you just wrap or just use the reader transformer from the transformers library, or just wrap everything in a reader? So why should we bake this R here? And so that's one question, and the other question is, why should we have these foreign pointer contents here? I mean, you should be able to just implement your parser if you only have 2 pointers. And the answer is that if you don't use the reader, so if you just say that your parser is simply just a parser with a unit EA, then it's so the reader arguments are going to be optimized away in a very reliable way. So if you have this definition, if you need the reader, then you can use it, and then it's very convenient. But if you don't need it, then if you only have this reader here kind of as a baked in function argument, then it's optimized away very reliably. But as soon as you try to use some kind of external reader wrapper types or the reader transformer, then it's going to be much less reliable. So I mean, that's just my experience in just looking at a bunch of GHC outputs. So like so that's the reason. I mean, it's very convenient if you need it. If you don't need it, you don't have to use it, and it has pretty much 0 overhead if you don't use it. And this is kind of similar because so the reason this is included is that if you want to get a byte string while you are doing parsing, then you can rebuild the original byte string using these addresses and also these foreign pointer contents, which is kind of just a finalizer for the memory allocation of your byte string. So if you want a parser such that you can always grab a byte string, then this makes it possible. But if you never have to grab a byte string, then this argument also gets optimized away, and you don't get any overhead from this function argument. Okay, and what about this distinction of the different kinds of errors? So this is not how it works in the Parsec libraries. And interestingly, but this is the way that the GNOME parser library works in the Rust language. So this is how GNOME in Rust works. And I arrived at this design independently of this GNOME parser combinator library in Rust, but it turned out to be that the approach is very similar, but quite different to how it is in Parsec. So because in Parsec there is a distinction between parsers that consume input and parsers that do not consume input. So there is a distinction. So consumes input and does not consume input. And if you have a parser which consumes input, then by default you cannot backtrack from the failure of that parser. So you can't backtrack from consumption, but by default you can backtrack from non-consuming parser. But it turns out, okay, maybe there are some people who are not closely familiar with how this works. So like for example, the way it works in Parsec is that you have maybe some kind of primitive token parsers. So you have some token parsers, and the token parsers, they don't consume, which means that they kind of fail in an atomic way. So maybe a token is just a single keyword, or it's just a single identifier, and then if the parsing of a single token fails, then to the outside it looks like that it hasn't consumed any input, so you can do a backtracking from it. So you can do something like a symbol of, or maybe let's call it a keyword of foobar, and then you can do this alternative choice between this parser and some other parser. So you can do maybe a foobar, and then if this is a token parser, then what happens is that first we try to read this, or maybe let's put something here. Maybe let's put oh no, this is already good. Okay, so if I have an input which is actually foo-bar, then first I try to run this parser and it consumes the foo, but then it fails at this point. But the failure is not really visible to the outside, so it backtracks to the beginning of it backtracks to the point where it hasn't yet consumed anything from this keyword, and then because it looks like that it hasn't consumed anything, we can just do a backtracking choice and try to parse this, and then we consume this foo once again, but then we can continue with this foo bar, so it kind of works. But if I have something which looks like this, so I do a keyword foo, and then I do a keyword bar, and then I do a keyword foo bar, then this actually fails because this is a token and this is also a token, but this monadic sequencing means that we have some reading which is committed. So if you read this keyword foo, then it's something which is committed, and now we try to read the keyword bar, but then it fails. But now we have a failure in a state such that some amount of input is already consumed. So then this choice between these two parsers also fail. So this would be an awk, and this would be a fail. And the way to kind of repair it is to say that this should be a try, and the try converts any parser which can consume input to a parser which does not consume visibly to the outside any input. So this is like an explicit keyword for permitting additional backtracking. And what I believe is the motivation for this kind of backtracking control is that so we want to discourage like unlimited look ahead. And kind of so the good implementation practice is to say that that only the very cheap token parsers, so only cheap parsers should be non-consuming, and everything else should be consuming. So this would be a good practice, but my experience is that this good practice kind of falls apart if you have a larger language implementation, because and actually just calling them consuming and non-consuming is kind of a misnomer, because what I care is not consuming stuff. What I care is the possibility of backtracking and the impossibility of backtracking. So this consuming, non-consuming distinction is pretty much just overridden by all of these try expressions. So this is most likely, I mean, kind of overridden, and so it does not really map to the actual parsing logic that I want in a parser. So there isn't really like a close correspondence between consumption of input and possibility of backtracking. So okay, so instead, what is a better solution in my opinion? So this solution is kind of good if you are writing parsers which are simple, and you don't have to think a lot. I mean, you have to sprinkle a bunch of tries whenever something does not work properly. And if you are writing a small parser, then it's kind of okay, because you start with this convention that only cheap parsers can be backtracked from, and then it kind of works up to a point. But at some point, you really have to think about like what is the actual grammar of your language and what is the actual control flow of your parser. And in any case, if you want to have good parsing error messages, you have to really think about the grammar, and you have to think about exactly where the ambiguities are and where you have to do lookaheads, and then you have to manually write a bunch of informative parsing error messages. And then this does not really play in a very nice way, because all of these tries kind of are throwing complications to your kind of parsing control flow. So this could be like good if your parser is very simple, but probably it's not so convenient if your parser is larger or more complicated. So the alternative, which is used in the non and flatparse, is to explicitly distinguish backtracking and non-backtracking things. So we kind of distinguish what we really care about. So, and the way it works is that there is failure, which is a failure for control flow purposes and can be backtracked from by default. And there is an error, and this is, so you should throw an error if you know that something has to be grammatically invalid. So whenever you see something which like it cannot be recovered from in any way, then you throw an error. So this is like a grammar error cannot be recovered from. By default, of course, there are always some kind of escape hatches. So there is still a try. So there is still a construction which converts an error into a failure. So, but by default, so this is the mechanism. And then like a very simple example is maybe if you have like a keyword one, P1, and then you choose the keyword to P2, then you want the keyword parsing in the situation to fail, but to not throw an error, because you only want to use these keyword parsers to disambiguate different grammatical cases. this would be like keywords can fail, but not error. In this situation, of course, sometimes you want keywords to also fail, like when I have something like a let and then something and then a keyword in and then a something. And in this case, this keyword should be a very strict thing, because if you have a let, then there must be an in. So in this case, this keyword in actually can only fail. And maybe let's put a tick here. So the keyword in can only, sorry, it can not fail but throw an error, natural error. So I think this is the classic situation when we have this distinction between error and failure, because here keywords are only used to implement control flow, but here this keyword is actually used to implement recognition of a grammatical construction rule. And as soon as we know that there is a let, we know that there must be an in. So there is no possibility of backtracking at this point. But then this means that so the implementer really has to think about what is part of the grammar and what is part of the control flow, and it means that like in many cases, like lots of parsers has to be available in kind of the error version and also the failure version. We can somehow try to structure the parsers such that to minimize this duplication, and this is like one of the open questions that I have. Maybe we can do some kind of simplification.
But can't you always turn one into another? Specifically, a failure should be basically an error parser is just something with a failure or something that throws an error.
Yeah, so there is such a thing, and I call it cut. So
it's not like you need two versions of everything.
Yeah, I mean it is always possible to convert a failure to error, and this is called the cut combinator. So it goes from a parser A to maybe some EA, and then we have maybe an error, and then we have another parser E of A. And if I do something like a PA of cut error message, if errors are just simply just strings, then what this does is that it converts the failure into this error message, and then I can have like a keyword in cut expected maybe in. And this works, but of course it's more convenient to have two different versions of keyword, such that if I use the cutting version of keyword, then I do not have to write this cut explicitly out in my parser. It's a bit more compact that way. And there are similar situations, like for different parsers. Sometimes I just have to define a short version of this cutting alternative implementation for the parser. And sometimes we even have to go a bit deeper. So sometimes it's not enough to just, if I have just any P parser, and in order to make it cutting, I just have to add the cut here. Because sometimes I want to have like a more optimized way of throwing error messages, and then it's better if I do not put the cut here, but instead I look into the implementation of P, and then I can do more precise cutting inside the P. And so it's not simple, and it cannot be done in a fully mechanic way. And I think there are probably some kind of abstractions which make this better, but in general I mean, like the fully mechanic naive solutions just don't work. So like this automatic hint propagation just doesn't work. This kind of consumed, non-consumed distinction just done naively, it also doesn't work. So at the end of the day, what we actually have to implement is to decide where to cut and where to put error messages. And so this kind of makes the job to do explicit if you want to do everything in a like production strength way. This is mostly my opinion on this. So this is a complexity which eventually you have to deal with it if you are writing a production strength parser. Yeah. Okay, so let's just look at what we have here. Let's go back to the parser. Okay, I will probably just be kind of short about the implementation. So we have this parser type, and then we have all these instances. And but I think it's important to note that this distinction of error and failure, it is extremely helpful for having good performance, because it means that that in the control flow we only have to care about failure, and it's very cheap. I mean, it's just a bare minimum that we have to care about it anyway. If we want to do any kind of control flow features, we have to do a pattern matching on a failure versus an OK. But we do not have to do any expensive operations on errors. The errors are just silently propagated, and we only do operations on errors when we have cutting. But but if you want to do fancy computation on these errors, like for example, we want to merge different errors together so that we can do like a trace or like a more sophisticated reporting of errors, when all of the errors like propagate to the top, then maybe I don't just want to print out one thing, maybe I want to print out multiple things, and then I can do some merging and some combination. But all of this code can be put into some kind of cold code, because I can just mark all of these functions as no inline, and they have a very low overhead whenever I have a parsing which ends in success, and I can make the overhead very low, and which is not possible, for example, in Megaparsec, when even if you have a parser which runs without errors, you still have a very high overhead of hint propagation. Okay, so we have like this functor stuff, and like this is just kind of a funny optimization. So if you know that X can only be an error, a failure, and you also know that these constructors don't depend on A, then you don't have to match on them. You can just unsafe coerce them, and it's slightly better in code generation. Okay, so we have functor and applicative, and you can see that I don't have to care about the error constructor anywhere. I only have to pattern match on the OK constructor. Okay, and there is also like a higher level data for results, which is pretty much the same thing, but it doesn't use like the low level hash types. So there is a parser running. So the way the parsers are run is that I just take a bystring and I just unpack into essentially the finalizer, and I have the length. So I just compute the start address and the end address, and I use this unsafe use as C string, which makes sure that like this finalizer does not really get garbage collected. I mean, probably it wouldn't get garbage collected anyway, because I'm passing this finalizer to my parser function, but I mean, this is the safe way to do it. It would be a bit irresponsible to not do it in a kind of a YOLO low-level way, when I just unpack this and just call a random function with the addresses. Okay. Yeah, and we can do like so this is just a reader stuff, and now we have like the empty is the failing parser, and this error is just a primitive throwing, and we also have this look ahead. So the fails, so this kind of converts a parsing failure to a success. So this try converts an error into a failure. So I mean, at this section we have like the different ways to convert between the different kinds of errors, or the different ways to throw errors. And yeah, we have the ability to convert an error into a failure. We also have the ability to convert a failure into a maybe. And here we have this cut. Okay, so question, how does PEG fit in here? So PEG is a bit weaker than, I mean, a bit weaker in terms of the expressiveness of the surface language. It's a bit weaker than what we have here. It's kind of, I mean, it's very similar. If you only use the applicative instance for parser and recursion and maybe try and cut, then you can implement any parsing expression grammar with my parser library. So my parser library is more liberal in what kind of implementations it allows. My library is just an arbitrary, it's like a generic monadic parsing library. Like you can write arbitrary recursive definitions and parsers. Yeah. So we have this cutting. So we have this cut, and we also have this this cutting. And the way this works is that we can give like an additional function which will be used to combine the inner error and the outer error. So the usual cut, it just converts a failure to an error. But this cutting, don't ask me about the naming of these functions. I just had to give some kind of name to it. So if I have a parser, and if the parser fails, then we just continue with this error. We just propagate this error. But if this parser throws an error, then we use this binary function to combine the new error with the old error. And this can be used to do this hint propagation if we want to do it. But then, of course, we have to do some non-trivial amount of implementation to make this usable for some very specific E error type. Yeah, so we have cut width to be similar with an union with, okay. Probably it makes sense. I write, so cutting should be cut width. Okay, and here we have like a bunch of primitive parsers, so we can parse, we can match on the end of the input, we can match on a concrete character and a byte and bytes and strings, but here we already have some fancy stuff. And the fancy stuff is that character parsing and string parsing is actually by template Haskell, and I don't think this can be sensibly implemented in any other way. So I think this is like a fully justified use case of template Haskell. And the way it works is that I have this string, and this string is a template Haskell function. And the way it works is that, so if you want to parse any string literal, then the template Haskell will generate kind of a vectorized reading code. So if you want to do something like a string foobar, then this is just so this is like 6 bytes. So 6 bytes can be read by doing essentially 2 instructions. So we do kind of right. So I can do just just a 4-byte read, and then I can do a 2-byte read, and but first I have to check that the input contains 6 bytes. And if I have something which also contains some Unicode characters, like if I put some lambda here, maybe, then I also know that this is 2 bytes. And once again, I do this optimized reading, but the template Haskell also performs the UTF decoding. And I think so this is pretty obvious that this should be the way to do it, and it's a huge performance increase compared to the libraries which don't do this. And I'm not sure like why on the other libraries don't just make it possible to write the keyword parsing like this. I mean, they do not have to make it mandatory, but probably they should make it possible to do it like this, because the performance difference is just really huge between this and just doing the UTF decoding at runtime and just working some kind of string at runtime by character, and then decoding every character and then reading that character from the input. Right, so this is how it works. And there is another kind of magic, and this is a bit low level. So there is this switch expression, which is also template Haskell function, and it looks like this. So if I write a parser which looks like the switch case of, so here this maybe looks a bit stupid, but what happens here is that I'm intentionally overloading the case expression of Haskell for this construction. And then I can do it like this. I can maybe also do a full bar here. And I can also do a default case. And the way this works is that I can switch on essentially just literals. So I can switch on string literals, but every switch is compiled to like a trie kind of structure. So this is going to be a trie of reads and comparisons, or okay, maybe not comparison, but just reads and case expressions. And like the keywords or the string reading, so this is also kind of vectorized using like the at most 64-bit reads. And we also have like this aggregation of ensuring that the input has enough times. And we also have longest match semantics. So we don't really have to care about the order of these switch cases because it has these longest matching. And you can view it as kind of a mini lexer generator embedded in your Combinator library. But it's a very kind of a stupid and simple one, and I played around for a while. So when I first wrote this library, I played around with actually writing a more fully featured lexer generator, which will make it possible to do not just this kind of switch expression, but to do a switching where all of these clauses can be regular expressions and not just string literals. So then it would be possible to have like case of, and then I can write a foo here, but maybe I can also write like something which looks like a literal here. And I think in many cases it would be very helpful and maybe even faster. I mean, not maybe, but certainly in some cases it would be faster to just write like a mini lexer like this, and then it can be compiled into a more general kind of finite state automaton, and not just a try structure of control flow. But when I looked at it, it turned out to be a lot more complicated than I thought it would be. So probably, yeah. I won't talk about it, but if you look at like the textbook presentation of doing lexer generation, then if you have Unicode characters, then there are issues which are usually not covered in textbooks. So Unicode plus lexer generation, because I mean, like in the textbooks, you have like an ABC, which is like the English alphabet, and you have many algorithms which work by, oh well, you should just iterate over all symbols, and then for each symbol you should do something, which works if you only have like the English alphabet, but it doesn't work if you have algorithms which should work over Unicode, because you cannot iterate over every code point. And then there should be some kind of restrictions, or maybe there should be some kind of predicate language, and then you have to somehow compile a predicate language such that all of your predicates range over the entirety of the Unicode range, and somehow try to minimize like the amount of work which has to be performed in order to be able to do queries like this. Or maybe you also want to do queries on Unicode character classes, but you don't want to do lots of Unicode character class queries, but then because it's usually the way it's implemented is that you have like a big array with a bunch of static data which is linked into your program, and then you just do some access into the big array, and then most of the time you want to avoid accessing the big array of Unicode character metadata and whatever. So it turned out to be like more complicated than what I thought it would be. So I just dropped this feature. But on the long term, I think it's a very nice feature.
Sorry, can I have a question? So I might missed it, but are you operating on UTF-8 encoded values, or you convert up to code points that are requiring 32 bits to store?
I mean, so the parser itself operates on bytes, and UTF decoding, whenever possible, is performed at compile time. But the car is actually it's a code point, because it's a 32-bit value. So if I program in car with Haskell, it's kind of a 32-bit, and it's just a code point essentially. So
I not think I fully understand it. So in my parser, I went with first going through the whole data and converting it to code points, and I don't really mind that it deflates, so it increases the amount of memory footprint, because then it at least has a uniform storage. And I was thinking about that during this first conversion step, I can compute some statistics that can be used later in allocating some temporary storage. My question is, are you using something similar to this, or you are converting locally when you need it?
No. I thought about this, but then I think it's probably less efficient. So the solution would be, is to you get an UTF-8, but then you convert it into just a sequence of 4-byte code points, and then you just parse the code points, and then you don't have to do any decoding, right? When you
But I think this is the same what we are talking about. So
yeah, I mean,
converting from UTF-8 to UTF-32.
Yeah, but it's not what I am doing. So what I am doing is that my input is UTF-8, and whenever I write a keyword like keyword parser like a string foo, then what I write here is in UTF-8, but the parser which is computed from this template Haskell expression, first it converts this foo to just a byte sequence, and then it reads the byte sequence.
And the compare is done as a byte sequence, right?
Which compare?
I think the key insight is that you never need to do UTF-8 decoding when you're parsing, because what you do is you do encoding when you're making the parser. So that gives you the bytes that you want to compare against. Right, but you never need to decode, because to parse. It's not like you want to know what are the characters. You want to know if the characters are
equal.
What the given parser requires.
Okay.
Yeah.
So you are just doing a byte-wise comparison, right?
Maybe I was using the terminology exactly the other way around, but yeah, I mean, if we have like a string like this, yeah, then you say that actually converting this to a sequence of bytes is UTF encoding, or what? I mean,
Let's not get into what is encoding and decoding. So
no, but I mean,
you are
the
trying
point,
to
right?
do...
That if we use the word correctly, then everyone will understand what's going on.
So you are trying to do an equality check on the smallest memory footprint representation. Is it right?
Yes, I mean, I don't touch the... Yeah, I just have UTF-8 input and
the comparison, when you are comparing foo with an actual position inside the source code, you are comparing it byte-wise in UTF-8. Is it right?
Yeah, so
okay.
Says encoding output is UTF-8, decoding input is UTF-8. So I think what I'm doing is decoding. That's why I was using decoding, because I have a string which is a UTF-8 string in Haskell, and I decode.
No, you have a sequence of characters. Your input is a sequence of characters. You're encoding it so that you get a sequence of bytes, because then you can compare that to another sequence of bytes, which is the sequence of bytes on your input.
Okay.
And this matches Balázs's terminology. Oh yes, yeah, he already wrote that. Okay, exactly. But I think there is one subtlety in this, in that this means that you assume that if you encode something in a given way, that's the only possible encoding of it. So if I have some crazy character which can be represented as some other character plus some combining symbol, right? So that means that this other representation could decode into the same character, but this parser is not going to pick that up. So it will be a mismatch, even though semantically it's the same string.
Are there examples for this in Unicode? Because if
well, I don't know anything off the top of my head, but Unicode is actually somewhat famous for this kind of BS.
Code and verse.
Okay.
So there are lots of combining diacritics and things like that,
but I don't want to care about this. So I explicitly don't want to support. If someone needs it, then they can do a pull request or an issue on GitHub.
Okay. So let's not go into deep into this, but there is another related issue: is the size or the number of characters. So if you are in UTF-8, the number of characters and the size of the encoding is not equal, and I wonder if it causes any problems.
Oh, because but again, if you're parsing, you only ever want to compare against some known string. So you know how many bytes it takes to represent a keyword that you're matching against, right? So either you want to parse up to a point, in which case you can formulate that point in terms of bytes, or you say, I want to match this particular keyword, but then you know how long that keyword is because you're encoding it before you are starting to run the parser. Like the whole thing makes perfect sense. You only need to know if you can still read, and that you can do on a byte length basis.
Yeah.
Okay. Hopefully there are no big pitfalls in this.
Yeah, I mean, yeah, that's correct, and that's kind of the philosophy. But if you are directly working with UTF-8, then what we cannot do in an efficient way is, for example, determine the length of a span in code points. So we have to scan it and do, yeah, so we cannot do it in constant time, and we also cannot determine the length of the the length in code points of the remaining part of the input. I mean, pretty much the same problem. And
this ties into the parsing errors, right? So you need the line character location for the start of errors and things like that. And I wonder how you are doing it now.
So the question is, how do we handle locations? And the answer is that we only even need the actual locations in terms of line numbers and column numbers in code points if we have an error. If we don't have an error, then we don't care. So
you compute back later on demand, right?
Right.
Okay.
So the way it works is that internally we only store, so we have, if we go back to this file, if we go here, and then we have pause. So we have this type of positions which can be used internally in the parser, and this is just a byte offset counted backwards from the end of the buffer. So it can be always computed because the end of the buffer is always available, current position is also always available. So this is extremely cheap to get, and we can also just store this. So a span is just a pair of byte offsets.
So sorry, buffer is a line, or what is the end of the buffer?
So what I get, so the input is a byte string, but the byte string is just a pinned memory buffer.
Yeah.
So
this is the whole source file.
Yeah, the whole source file is just a single memory buffer which is contiguous,
and you know its size and it does not change, right? So that's why you can compute
backwards. Yeah, I mean
backwards.
it's immutable. We don't do anything with it. We just read from it.
Yeah, and what is the logic for computing backwards and not forwards from 0?
We can go backwards. I mean, in general, it's kind of an unsafe operation, but you can do some computation where first you get a position, and then you do some parsing, but then you want to go back to the position. In general, it's unsafe, but in specific cases, it can be safe, and you can do it.
But why it is better than going forward from the 0 position?
Oh yeah, because we do not have the 0 position in the parser definition. So we have a new type parser, and this is the end of the buffer, and this is the current position during parsing in the buffer, and we have no idea about the beginning of the buffer because we don't care about the beginning. I mean, so this foreign pointer contents, it also does not contain the beginning of the buffer, but is just the way it is implemented in Haskell, that you can always just create a slice. So this is kind of just a resource manager for the memory location, and you can just create, you can just grab these 2 pointers and create a slice which has the same underlying buffer, but which is a different slice than like what you started with when you started parsing.
It's a bit strange to me, but let's not get lost in it.
Yeah, I mean, but it turns out that actually we almost never care about the beginning of the buffer when we are doing parsing. As you said, we just move forward and sometimes we move backward, but then whenever we want to move backwards, we have to grab some specific position to go back to. Yeah, so we have these positions and spans, and then the way it works is that we throw some error, and if we want to print the error, then we have to compute the line and column numbers. But I mean, it can be computed extremely quickly, and actually I have some slightly optimized function for this, which is called no, where is it? Yeah, so I have this function, and so this pose line calls. So if you take a by string and if you take a list of positions, then for every position in the list, it gives you back the real source position. And the way it works is that I'm just doing like a single linear parsing pass over the by string, and I'm just counting the new lines and the code points. And that way, if someone wants to compute like multiple 2 source positions simultaneously, then they can put all of these positions in the list, and then we can do it in linear time in the original source file. So I mean, even more naively, we would just recompute it for every single position, but then it would be quadratic and it would look a bit ugly if I only exported that function from here. Yeah, so is there anything else? Yeah, so here I have some combinators, and the combinators are, so there are slight differences from Parsec. Maybe this character parsing, it could be also a slightly interesting. For example, I have like the specialized functions for the ASCII range, because for example, if you're only parsing ASCII and then you want to do like the usual satisfy function, then it is much faster if you do not want to do a UTF decoding just for the sake of doing a satisfy. So the satisfy ASCII is kind of, you give it a function which is a predicate, but the predicate such that it only returns true in the ASCII range. And if this assumption holds that this predicate only returns true on the ASCII range, then we don't even have to do UTF decoding, so it's much more efficient.
So this predicate is usually an in-range check or something more general or complicated?
Usually it's an in-range.
Okay.
Like you want to do a digit, and then you say satisfy ASCII and then an is digit.
Yeah.
But the is
Fine.
digit is not the Unicode is digit, but it's just the ASCII from 0 to 9. And then the satisfy ASCII would be a good way to implement that, and it's much faster than doing the full.
So
full
I
UTF.
started with the same approach for my parser, and then I'm not convinced that it is the best approach. So later so now I'm switching to pre-computing things like this, and it's right that we don't want to enumerate the whole UTF plane, but we can split it up into like 16-point chunks and pre-compute all these predicates, and then we can use the index of characters as a lookup into these pre-computed values. Because if these range checks get more and more complicated and more dense, for example, we have Greek letters and things like that, and we would like to filter them in a way, then it might be actually faster to just look it up than doing the comparison.
Yes. So this
The
is
question is, were you thinking about something like that, or do you have any
yeah, so
ideas or benchmarks?
So this is related to what I was talking about here, is that I want to have, ideally I would have Lexer generation with regular expressions, and the regular expressions can include Unicode predicates. And I want to have an optimized compilation of Unicode predicates into some Unicode range checking. Right?
And you are doing it with template Haskell, right?
And the answer is I'm not doing it at all at this point.
Okay.
And so this is the part which seemed a bit complicated, and I did not really need it, and I'm not doing it. So now I'm just doing some very simple things which allows you to write like more optimized Unicode predicates by hand. So,
Okay.
So this is called the fuse satisfy, and the way it works is that you can give it 4 functions, and the 4 functions are in the byte size range. So you have one function on the 1 byte range, one on the 2 byte, one on the 3 byte, 4 byte, and so if you want, you can write an optimized Unicode predicate by hand, and these 4 functions essentially allow you to inline a predicate into every part of this UTF decoding function. And I benchmarked it, and sometimes it helps a lot. So it increased like my overall parsing benchmark speed by something like 30% if I use this fuse satisfy for actually trying to recognize Unicode letters. So an example for this.
So it can take a look at 1 or 2 or 3 or 4 sequential bytes and evaluate the predicate on them.
Yeah, so I can do like a fuse satisfy, and the fuse satisfy gets 4 functions, but here I can just write an is Latin letter or an is ASCII letter, which is super simple. And then the way this function works is that if I have a code point which is 1 byte, then it just checks for this, and then if it's 2 byte, then it checks with F, and it checks with G, and then it checks with H. And if I know that in my source file like 90% of the characters are actually ASCII letters, then I don't want to call these functions, because these functions are at least in the Haskell standard library, so these are accessing the big Unicode character class table. And and I benchmark this to be a big boost in performance.
Okay, so then it is an early exit check, right? So
Right.
90% of the cases is ASCII letter will return true, and you can early exit from the comparison or the satisfaction function. And if it returns false, then you keep on checking with the other ones.
Yes.
Okay.
And then if you want to be even cleverer, you can also include this could be just do checking for things which you know to be frequent, like Greek letters, for example, and then you put is Greek letter here. C, and then you go back to like the full Unicode is letter C or something like this. Yeah, so and you can see that I'm using like this digit, Latin letter, and Greek letter. It's very, very simple functions, and here have a bunch of combinators. So the combinators are probably not that interesting. We have these positions. We can get these spans, and we can turn a span into a bystring, or we can run a bystring and then return, like run a parser and return a bystring which contains like the span which is consumed by the parser. So we have all these operations, and generally these are quite fast because I can create a bystring by just essentially putting the finalizer together with the 2 pointers which mark the end and the start of the slice. Yeah, and then I have so these are just a bunch of unsafe functions, and this is like for the template Haskell, so I'm trying to convert everything into these unsafe scanning operations. So like the scan functions, they don't even check that there are enough bytes in the input, because we assume that this is just part of the template Haskell code output, and the code output explicitly inserts the checks which ensure that there are enough bytes. There are a bunch of scanning functions, and this is kind of just the way to generate like an optimized sequence of scannings, and then here is some kind of code to generate these case try switching expressions. So I just define a try, and I do a bunch of passes on this try, and then I generate some template Haskell code. Okay, so this is the library, and this is the basic stuff, and the non-basic stuff. So this stateful. The only difference is compared to basic, this just has a single int hash state. So usually we would only have like a single pointer, which is the current position in the parser, as a state component, which is threaded through. But now we also have an additional int, and the additional int can be used to store information about significant white space. But I mean, in principle, you can use it for whatever purposes. But I think usually you would use it to implement some kind of indentation parsing. And it's exactly the same code, and actually it is just copy pasted over, so the entire thing. And whenever
I have a question. So if the state is there so that the user can use it to track indentation, but you don't track indentation yourself, then why is it an int and not just anything?
Because if it's anything,
Why is it not polymorphic?
Well, because I mean it cannot be representation polymorphic. If it's polymorphic, then it has to be a boxed thing, and that would be a big overhead on the overall performance. So if I just pick int hash, then I think it's probably enough for every kind of imaginable indentation tracking. If I just say that it's just as s, which is a state parameter, then I mean, unlike with the reader components, so you can always just add more and more reader arguments to the environment, and GHC can optimize them very well, but you cannot add arbitrary state components because GHC is very bad at optimizing them. It cannot turn a boxed int into an unboxed int if you put it into a state. And if you try
So the problem is on the return side of the function?
Yeah, the problem is exactly on the return side. So you can see that this is a result, and here I have an unboxed tuple. I cannot say that I have an s and I put an s here, because then it's not representation polymorphic. It has to be a boxed thing, or it has to be something with a concrete representation. But then, I mean, I cannot write so-called levity polymorphic code because then my library function just stopped working. They just don't type check because there is no such thing as a true levity polymorphic function in Haskell. So I just have to pick one representation, but I can just pick int, and then int, I mean, the intended purpose is indentation parsing anyway, and int is enough for any kind of indentation parsing. And in the hypothetical staged language, this would be also just I wouldn't have to do this magic. This would be just normal types and just normal polymorphism, and it would work nicely, but not in Haskell. Yeah. Okay. Maybe we can look at. Maybe so what I have, so I have like this this basic lambda example, and just very quickly we can look at it. So this is kind of a simple lambda calculus parser, and it has an implementation of error message propagation. So the way it works. So the reason this is not in the library itself, it's only in the example, is because I haven't yet figured out a reasonably good generic way to do it. So it's still kind of open question how to do it, which covers enough use cases. But here what I'm using is that there are some kind of expected items, and expected item can be just a concrete message, or it can be a literal expected thing, like a keyword or something like that. Then a parsing error can be a precise error and imprecise error. So a precise error is like leaving out the in from let, and in this case I do not want to inundate the user with like all of these expected things, because there is a very concrete problem in the source, which is that there is an in which is missing from a let. So I only want to report that very concrete, very specific error to the user, which can be or should be fixed. And that's the reason for doing this distinction. So whenever I'm sure that there is a very specific error, I just print out the specific error. If I'm not sure, I have like a range of different things which could have been written in the source file, then I return this imprecise. So then I have a list of expected things, and then I have this merging operation. So I can merge errors such that, so first I try to merge them by looking at the error positions. So whenever I have an error which is like, which consumed more input, so a parser can like consume some amount of input and then throw an error. And I want to, so I want to kind of propagate the errors which are the most specific, and the errors which happen like further along the way of parsing are more specific than the expected things, which are kind of like more generic and more fuzzy. So this is kind of a first check, and then if the source positions are exactly the same, because I get multiple errors without having consumed any additional input, then I just do this kind of merging, that the precise is always preferred, and if I have two imprecise things, then I combine the imprecise expected items together. So this is just like one possible solution which I implemented, and it seems to work fairly nicely. And you can also see that this is no inline merge, because so this is cold code. So I do not want to inline this thing into my actual parser, because this should be out of line. Yeah, and then I have
sorry, but I didn't get that explanation at all. It sounded like you were saying that it shouldn't be in line because it shouldn't be in line.
I mean, it shouldn't be inline because performance is about parsing files which are syntactically correct, right?
Okay, now I get it. So you're saying that it's not on the happy path. Basically, that's what
Yes,
you're
of
saying.
course.
So if we get here, okay, yeah, right, okay.
Yeah. A pretty error. And then I'm doing just a bunch of wrappers. So it's a bit confusing now. So I haven't yet finalized the implementation here. But the point is that I'm just writing a wrapper for the cutting. So I have this cut, and it just slaps a bunch of imprecise expected items to what error is returned from this parser. But here you have like this more precise cut when we propagate at most a single error, because we wrap this error in this precise constructor. Then you have a bunch of wrappers on runners, and then we have the white space parsing. And I think it looks pretty nice. So you can see here that I'm using the switch expressions. So this is the white space parser, and then I'm switching on all these different white space characters, and I have also line comments and multi-line comments. And yeah, so this is like the implementation of white space parsing, and it's actually it's really fast compared to the different parser libraries. And you can see here that I also allow nested multi-line comments, because here I'm counting the nesting level of the multi-line comments. Okay, and here then I have a bunch of wrappers on symbols and keywords. And you can see here that I have just a function which is called isKeyword, and this is like a really efficient way to test whether an identifier is a keyword. I mean, usually we want to disambiguate the identifiers and the keyword. So an identifier cannot be a keyword. And the way I will do this testing is that I just call this isKeyword function on the span of my identifier parser. And this is also super fast compared to whatever solutions you find in the other libraries, because it's just compared to a bunch of machine code which does like a try of comparisons here. Yeah, and then I have the symbol and the symbol prime, and I have a keyword and the keyword prime. And the way this works is that the prime is the error throwing version. So the prime parsers are like cutting. So if I do a symbol prime, then it throws an error. But if I do a symbol, then it throws a failure. And likewise, keyword is the failing parser, and the keyword prime is the error throwing parser. And if I go to this parser file, then I have the same distinction, is that the prime is always like the strict parser which throws an error, and then non-prime is the version which throws a failure. So you can see here that an identifier is it's a token, and it's a byte string of, and then this is the actual identifier parsing, but it only returns a unit, and what I care about is just the span of this parser. And then I have this combinator called spanned, such that this first parser runs, and then I can actually, if I do not write it in a point-free way, then it looks like this. So what it means, that is an identifier is just this, such that it is not a keyword. And I check that it is not a keyword by using the isKeyword on the span, and then calling the fails, and the fails is the function which converts a failure into a success. Okay, so this prime version, it does this error throwing, and I have atomic expressions, so it can be in an identifier, boolean, int literal, or it can be a parenthesized expression. And here you can see that on the left side I'm using the symbol for the opening parents, but on the right side I'm using the symbol prime, because at this point I'm sure that there should be a closing parents, and I don't want to backtrack from this reading. And here I'm also using the prime version of tm, because I know that there must be a tm at this point. If I already know that there is a parent, then there must be a tm after that. And then I have some applications and some multiplications, additions, some comparisons, and this is just a recursive precedence parsing. And then I have a let, lum, and if. For example, in this let you can also see that I'm starting with a keyword which can fail, because later I will just do a choice between these different parsers. So I want to do a control flow switching on the first keyword here, but all of these things are completely fixed, so they are the error throwing versions. And then I have this tm parser, and actually I'm only using the tm prime parser, and in the tm prime parser I additionally slapping this the list of expected items here. So it looks kind of reasonably. It could be even faster. So instead of using these choices here, I could also do like a more low-level switch expression. But the switch expressions can be a bit noisy and annoying because they don't really play along well with the token parsing conventions. So I already defined that the keywords and the symbols and the whatevers, they should all eat white space. But I haven't yet implemented any nice abstraction on the top of the switch construction, which would also make it possible to integrate white space parsing into switch expressions. So if you write a switch, then you have to manually write white space consumption after the switch cases. Right? So this is how it works. So this could be optimized, but if you just write it in this way, which is I think fairly idiomatic, then it would be like way faster than pretty much any parsing library, and I think it looks kind of reasonable. So I can also look at some benchmarks. So I only did like one larger benchmarks and a bunch of small benchmarks. So the large benchmark is that I already have I have this multi-t parser, and which is Megaparsec, and then I wrote the separate tt parser, which is in flatparse, and which is a superset of small tt syntax. So it's not a fair comparison, because the separate tt parser is more complicated because it is a significantly larger syntax, but it includes essentially just the small tt syntax. So what I did is that I benchmarked like this on a 10,000 line file and this on a 100,000 line file, and then this was about 30,000 line per sec, and then for 35,000 line per sec, and this was about 1.5 million lines per sec. I mean, but this is a bit unfair to Megaparsec, because Megaparsec is really bad at handling indentation and source positions efficiently. So, but I mean, it's a feature which I want to use. So in that sense, it's a fair comparison, because I really want to have source spans and indentations. So I just want to do it, and then I also have some benchmarks in the README, which is more like micro benchmarks. So these are all just several lines. So here this is a parsing of S expressions, and you can see that So this FP basic is the flatparse basic, and this is the stateful version. So this is a 3.3 milliseconds for flatparse and 5.6 milliseconds for bytesmith. So bytesmith is quite good, but you can see that Megaparsec and Untitled are about 10 times slower than even that. And Parsec is even a couple of times slower. And this is just parsing some long keywords repeatedly. And you can see here that this is like 0.3 milliseconds for flatparse and 50 milliseconds for parsec. And we have some comma separated values. You can again see that this is like 0.8 milliseconds. And already for Megaparsec it's 10 milliseconds. Yeah, there was this issue, but it seems that I have prevailed. I mean, it's not conclusive, but I really think, I mean, there should be a consistent advantage flatparse should be consistently faster. I mean, I looked at the implementation of bytesmith and it just has more overhead in the internals than flatparse in general. Yeah, and another interesting metric is if you try to compile this, then like what about the compile times and what about the code size? And again, you can see here that the code size is pretty good here with the flatparse. So I only have 26 kilobytes with the basic flatparse library for these benchmarks, so all of these 3 benchmarks. But with Megaparsec, I have 188 kilobytes for exactly the same thing. And we can also look at the dumps. It's kind of interesting to look at this dump LLVM and dump SCG and dump simple, so just dumping all the intermediate representations from GHC. And if you look at this FP basic dump simple, then here we have some kind of gunk related to template Haskell. But after we go to the actual code, then you can see that this is like less than 500 lines of GHC core, which is output from this benchmark. And then if you look at the functions, then you can see like this very, very nice stuff. For example, like reading these long keywords is just and you see like I just have a bunch of integers which are computed by template Haskell for this vectorized reading. So I just have a bunch of vectorized readings and basically have 2 pointers as input and have 1 pointer as output. So it looks really nice. In comparison, if we go to the same thing, like the dump simple for Megaparsec, you can already see that it's about maybe a bit less than 3,000 lines. So one was about like 500 lines and the Megaparsec is about 3,000 lines. And if you look at the Parsec dump simple, then you will see horrifying things, as I mentioned before, because you can see, I just give some good example. You can see that you have worker functions where even the monad methods are not inlined. So I don't even understand how this is possible to just write a bunch of parsers and then you have the monadic bindings and the monadic returns called actually as projections from a dictionary. Yeah. And it's also quite interesting to look at the LLVM dumping things, but probably we shouldn't. And I think, but this is a good illustration for how absolutely horrible the LLVM backend of GHC is. So one quite brutal example to this is that where where is it? It's not in bench, but in the source. Okay, it's not there because probably I just cleaned it up at some point. But the point is that I have this basic.hs, which is about 1000 lines of code. So this is just a single file with about 1000 lines of code, and it is very, very low level. So the only complicated thing which I am using in this file is just 100 or 200 lines of template Haskell code for generating these try switching expressions, and this code, it's also just pretty straightforward. I mean, it only uses the map as a data structure and maybe also the set. So the only dependency of this file is the containers, and the rest of the code is extremely low level. It just uses primobs essentially, and no abstraction at all. It's just completely monomorphic code using primobs. And if you translate this file to LLVM, then the size of the output is 250,000 lines of LLVM IR. So we get a 250 time blow up when going from this file to LLVM, which would be reasonable for some super high level module, but even for this super low level module we get this 200 plus times instructions for every single line of this, which is, I think, probably a bit excessive. Yeah, so time's over. I didn't talk about how to actually implement indentation parsing with the extra state, but maybe we can just skip that. I mean, the point is that you want to count relevant white space, and it depends on what is a relevant white space. Okay, let's just quickly summarize. So how to indentation parse. So we can have that if the leading white space is relevant, then you just have to write a white space parser which counts code points after new lines. So we write this parser which counts code points after new lines, but which kind of resets the state to 0 whenever we have a new line, and then we start over counting the code points. So if the leading white space is relevant, then I think this is the absolute fastest implementation, and we don't have to track line numbers and column numbers in the parser anywhere else. We only have to do this addition to white space parsing, and it's efficient. But we could say that if columns are relevant, but I think we should probably just avoid this. I mean, usually by indentation parsing we mean this. So we mean that leading white space is relevant, and we don't mean that exact columns are relevant. So this would mean that we can do something like a full bar bus in one line, and then we have to exactly do an aligned line for a full prime, bar prime, and bus prime in the next line, and this would be like a relevant column numbers. But usually this is not what we use. What we use is that only the leading white spaces are relevant. So I can do a case full of C1 and C2, and we only have to look at the white spaces before these clauses here.
But don't you need more state than just the int you use to compute the first column? Because for indentation parsing, basically you need to know that the C1 and the C2 aligns.
Yeah, but
right at the start of the line.
Yeah, and the way you do it. So if you want to do,
are you using the closure of the bind bit to do that, or?
Okay, so So like this exact alignment is a slightly more complicated feature, but the way you do it is that you parse the C1 and you remember the column as the C1, and then you just insert a guard for every subsequent clause that checks that the column of the other clauses of the
Right. I think that's what I meant by using the closure of the bind, because in effect you have extra state in this case, but it's in the closure that is on the right hand side of the rest of your do block.
Yeah, so yeah, I mean, if you want to do exact alignment, then you have to use, as you say, monadic bind to remember the position of the first one and then align everything else to the position of the first one. But this is not the most common case. So usually in indentation parsing, like most of the overhead is that you want to check that like everything in an indented block is indented. So every single token is indented correctly in the block, and you even use indentation to do kind of like a separation of different parts of your code from each other. Like if you want to do a top level definition, then you do like this, blah blah blah. And here, even if you only want to do a top level definitions with indentation sensitive parsing, then you have to make sure that if you do this kind of definition, then it's still valid because this is indented. And even if I write like a more complicated expression like this is also valid, and this is also, but this is not valid anymore because the Z token is not indented in the right region anymore. So most of the overhead is that whenever you read an arbitrary token, you have to do an indentation guard condition. And if you want to do that efficiently, then there really should be the state component in your parser. And if it's just an unboxed int, then you can access it like efficiently. And this is like a more complicated use case when you want to exactly align, but usually you just want to check that like there should be a reader component in indentation parsing. So there is a reader of like current level of indentation, and then there is a state of current leading number of white spaces, and then you have to compare these two. So if I have an X here, then I know that the current level of indentation is 1 because everything after the top level definition should be indented, but I also know that the current leading number of white space is also 1, so it's okay. But if one is smaller than the other, then it's not okay anymore. Okay, should we finish? Any other questions, comments? If you want to have more than 64 bits, then you can do a pull request where you you had 128 bits instead of 64, and just add a new module which is exactly the same but twice the number of bits. Question is, do you literally copy paste the source code? I did. There is an issue which I personally wrote, which is about this code duplication problem. So there is an issue which says that I should deduplicate the source code between the two modules. But on first approximation, it was it's just I just started with a single file, so I just copy pasted and I just adjusted the code. So that's how it was written. And because the change is completely mechanic, it was very, very quick to do it this way, but it should be somehow deduplicated. I agree. I mean, in Haskell, like one of the potential solutions would be to abstract over it with a type class, but I don't have that much faith in JHC to do that kind of solution in this library. So I think I could do this type class solution for the template Haskell part, because in the template Haskell implementation, it doesn't matter if I use instances, but in the actual parser code, I don't want to put instances there because it's not
you
robust.
can generate the source code from the same source somehow, but it's ugly a bit. But better for maintenance.
You're short of macros.
Sorry, I didn't hear very well.
You're short of macros. You need macros to generate code for proper metaprogramming, but I'm not. Maybe template Haskell is good enough. I don't know.
You see, yeah, I mean, so the ideal solution would be to write the same library in the future language, where I have staging and type macros. I mean, it would not even be a macro, it would just be a normal library with some polymorphic code, and it would be compiled to the maximally efficient representation.
Then just mark it in a comment, and then you bootstrap the stuff, and then you get it.
Yeah, that's what I'm working on right now.